thank you for the introduction, and thank you for the invite, not just to come here and pick up this cool hand that you guys built, but also to tell you guys a bit about our work on hybrid AI for safe embodied intelligence. So first, what are we talking about here when we talk about embodied AI? Embodied AI is a somewhat new-ish term, or at least it became very popular recently when people talk about the intersection between robots and maybe the way that roboticists still think about robots and agentic AI. And now embodied AI is anything between that basically has a physical body and is in somewhat artificially intelligent. This encompasses drones, it encompasses autonomous vehicles, but also crucially encompasses robots. And I don't like this slide because it only says humanoids, but actually embodied AI is basically any robot that is in some way intelligent. And so what's a bit of a more rigorous definition, right? So we can go back to Newell, who said that an agent is a system with actions to achieve its goals based on the knowledge that it has. And actually, goals are knowledge too, right? Like goals basically are just the knowledge about what you want to achieve, either the agent itself or maybe the person who's programming the agent. So what does that have to do with safety? Well, for an intelligent embodied agent, three aspects are very safely relevant. One of them is that, yes, it is an embodied agent, right? So we need to think about how can we competently interact with the physical environment without breaking it, or crucially, without hurting people with our physical, just by being in the world, by acting, by running into them, by driving over their pets and so on. But also this idea of autonomy, right? An intelligent agent is only truly useful if it behaves in an autonomous way. So it has to make informed and independent decisions and adapt to its environment. If it doesn't do that right, A, it's not very useful to the people that want to use it, but B, it's also going to be potentially highly unsafe if that autonomy is not done in the right ways. And then the third one is cognition, right? So for an embodied agent to be safe, it needs to have a true understanding of its environment, right? It needs to be able to reason, interpret its own actions, and so on. Otherwise, we cannot really meaningfully speak about safety if the system does not have some form of capacity for understanding. Now, we all know that if we want to make agents act in the world, right, we want them to achieve goals like filling a cup or placing a thing while avoiding certain things that we don't want to happen. And this, in the beginning, seems like a very easy problem. If you maybe, I don't know, you're like taking Robotics 101 and you hear what an embodied agent is, think, oh, this is easy, but actually no, it's like an iceberg, right? You have all of these things that are under the surface that you don't even in the beginning see yet, but when you actually try to do things in the real world with robots, you notice that suddenly things are not so easy anymore, particularly when it comes to safety and when people are involved. So just take this very simple use case here, right? A robot wants to pour coffee into a person's mug, and well, you know, it's kind of easy to specify you want to pour the coffee without spilling. This is sort of a functional requirement. You want all of the liquid in the mug and none on the floor. But actually, what the robot should really be doing is it should not be pouring hot coffee into a cup that is being held by a person like this, because if something is spilled, then you're going to burn the person. So probably you should actually ask the person to put the cup on the table and then do the pouring there. But this is a thing that's requires actually a lot of this hidden, like this kind of reasoning requires a lot of this hidden capacity that robots need to actually behave in a safe way. Right? And that's, of course, understanding the action itself, what it means to pour a hot liquid. Right? It involves then prediction and experience. So you need to predict what happens if I pour the hot liquid, and experience of like, have I poured this in the past? Like what happened in the past? You need adaptation, causation, recovery, right? So if something goes wrong, a lot of safe behavior is also behavior that fails safely, and that way you can recover from failures and get the system back into a safe state if you sort of left it temporarily. And then, of course, the sort of one of the hardest things here is generalization to completely novel task situations and actions. Like imagine you're a robot who's never been asked to pour hot coffee before, but you're supposed to be autonomous and general purpose. So now you're face yourself with this task. Well, how do you do that if you don't really have, if you haven't done that particular task before? Right? And there are certain requirements then to safe robotic agents that we need to think about. Here, for example, you see our PR2 cutting a zucchini, and this is perfectly safe behavior in the context that it is, but if you put that same robot with that same knife into a room full of children, then suddenly almost any behavior the robot is doing with this knife is going to be unsafe. So safety is context dependent, and you need a lot of cognitive ability to understand that context, right? So there is sort of in order for a robot to be safe, it has to have considerable cognitive abilities. This is the perspective mainly from which we address safety. It's going to come later. And this is related to this idea also of like the dark matter of perception, right? This in this dark beyond deep paper, they were saying, for example, that perception actually is not just about understanding or perceiving the geometry and colors and so on of the environment, but also of all of the sort of hidden functionality of the environment, the physics, like intuitive physics of it, the intent of people and agents that are in the environment, or things like causal behavior that all play into safety. And it requires a lot of cognitive abilities to understand this, to parse this latent information that is in the world. And then robustness is another thing. So for an robotic agent to be safe, its behavior must be robust, because otherwise, if it is not predictable and/or repeatable, so if the robot doesn't reliably do the things that it's supposed to do, then how can it be safe? You cannot trust it, but also it's very hard to call that behavior then safe. Generalization is one sort of newer way that people are looking at this in terms of robust generalization. So it's kind of relatively easy to make AI systems that generalize in 90% of cases reasonably well, but then fail catastrophically in the sort of long tail, and that is still very hard to do. Another thing that maybe we out of the traditional robotics community don't really think about as much, but that the AGI community is thinking about a lot, is alignment. So you want your AI systems to understand human goals and preferences and select their actions in according to the human goals and preferences and not some other possible goals and preferences. Like here, for example, well, if you train an AI system or that's then controlling a robot to like never allow harmful prompts. Like basically you want the robot never to become like a weaponized system, and then you can jailbreak it. I recommend reading this paper. It's very interesting how they jailbroke LLM-controlled robots. And suddenly it's possible to just tell the robot to deliver bombs, and the robot just willingly do it, even though it has been trained with very different goals, right? So it's kind of very easy to subvert the goals that the robot has been trained for. And implant other goals and then have the robot actually choose its actions based on these new goals that are not aligned with the designers of the robot. So some applications. One of them is safe human-robot collaboration. For instance, we're very interested in this, particularly now that humanoids are actually being deployed in people's homes. And this is going to be increasingly important, right? Not just for functionality, but also for trust. Intelligent autonomous systems, like that's an interesting part that we actually don't really do much research into, but that we are increasingly beginning to talk to other people and institutions, also at TU Hamburg, ethicists of AI, who are very concerned about the fact that potentially we are going to have almost like weapons of mass destruction if you replicate a lot of autonomous agents. Then basically you can scale autonomous killing very easily, right? So these are two different problems. One here, the robust generalization is much more important. Robot must understand what it's doing. That's kind of what we are mainly concerned about, that aspect of safety. So robustness and understanding. Over here, we are running much more to the alignment and sort of provable guarantees problems that you need for these kinds of things. If you start to deploy autonomous intelligent weapons in the field, you want to make sure that they really behave only the way that you want them to, and not in some other way. This already we have, but here. So our thesis is basically kind of twofold, right? We want to make embodied agents safer by A, making their knowledge transparent, and B, by making the mechanism of action selection controllable, robust, and transparent. This kind of follows directly out of this definition of an embodied agent from Newell. Yeah. So who are we? At the AICOR Institute for Artificial Intelligence, we're about 30 people working on all kinds of robots. We have, I believe, 8 different robots, 5 mobile manipulators, and a few like single and dual arm setups in various different environments. So here you see kitchen and retail environments. We also have perfect digital twins of these, or as perfect as they get right now, digital twins of these environments that we build and test our algorithms in, and that we actually also provide under the virtual research building to our collaborators, such as all of the institutions in RIG. Yeah, so what do we want to do? We want to basically understand everyday activity as a computation, or we want to build a computational model of everyday activities, drawing interdisciplinarity from robotics, from the AI communities, from human action science as well, and build robot agents that can then do this and also provide these robot agents to the world in form of open source software. And we really believe that, you know, it really helps a lot to understand things like intelligence, things like safe behavior, things like human-robot interaction by building technical systems that actually do that. And I think you guys are also very much in the same boat here. So I kind of want to skip this slide. Yeah. So what we build is a hybrid cognitive architecture increasingly. So you probably know, or you've been exposed to the CRAM architecture and even the CRAM2 architecture, which has been augmented by several capabilities such as metacognition. But what we're now looking into is how can we basically build a third generation of this cognitive architecture that allows us to combine the advantages of pure symbolic reasoning with generative models, neural networks, deep learning, and so on, in a principled way, right? In a way that makes sense. And we kind of want to attack this in 2 ways, right? So a hybrid cognitive architecture should, should be deployable in all kinds of environments and all kinds of robots. That's kind of what it already does, so we kind of tick that box. But the idea is that basically we're going to have interpretable representations between hybrid modules, right? So we want to have modules. So for example, a perception executive should be able to use state-of-the-art generative models and so on. But even if they're not interpretable, the output of that module can very well be interpretable if it is, for example, a semantic scene graph, and we're going to get into that in a second. So you can introduce safety if you have a cognitive architecture, which is a great advantage over end-to-end models at the intersections between different cognitive modules, between different cognitive functions. And we're going to increasingly build the architecture around this principle, introducing generative or deep learning, non-interpretable, potentially unsafe functionality in parts where we can still control it by modularity and by having representations in between that we can understand and verify. Right, so these are the 2 hypotheses that we have. Implicit representations that make mental states, or what we call belief states, transparent. So we want to be able to show to the programmer or the user of the robot what the robot is actually doing or what it is thinking about. And we want to have hybrid symbolic and subsymbolic data instructions and algorithms that actually allow us to use these explicit representations in computations that allow us to then do cool things in the world. Yeah, and so the idea is that we want to build safer, more transparent alternatives to large-scale end-to-end neural architectures. So one thing that we're fundamental, like basically one of the two main pillars of this strategy is interpretable belief states for intelligent agents. So for us, the way that we push for safer robot intelligence is that we want to make the belief state of the robot interpretable. Right? The idea, of course, of interpretable AI or explainable AI has been around for a long time, but in robotics, this runs into certain kinds of challenges, and we hope that the technical contributions we make help, particularly the robotics community, to build these kinds of interpretable representations for robots' internal states. This is kind of an old idea, right? So already in 1943, Craig basically said that the brain is building mental models that support inference by mental simulators. He called this world models already, and the term world models is very in vogue right now, of course. But there's this whole idea by Tenenbaum a few years ago, who basically said that, okay, there are mental mechanisms that kind of work like game engines in humans' heads, right? And that allow us to, for example, use intuitive physics like a physics engine in our head to compute this future state of the world, right? And so, for instance, if I look at this water cooler over there, I see that the way that it is balanced, it's probably not going to fall over because it's, I kind of know that unless someone pushes against it, it's going to stay stable. Or if you make experiments with people who look at these kinds of structures here, there are actually a lot of interesting sort of cognitive science experiments about this, where people can pretty accurately predict in what direction a tower is going to fall if you remove one of the pieces, right? This is purely intuitive physics. We don't necessarily solve the differential equations, for instance, in our head as we compute where this tower is going to fall. But we can simulate the world ahead well enough to be useful. So this is this intuitive physics engine idea. And our idea is, okay, well, what if we actually gave robots literally a game engine in their head? And we represent the world as semantic scene graphs. And we can then render these semantic scene graphs and interact with them. Right? So what if we actually make the mental belief state of the robot a thing that we can visualize, that we can press play on, that we can simulate into the future, that we can change as humans by stepping in VR into the robot's brain and literally taking the things that the robot is thinking about and moving them around and teaching them that way. Or asking it questions interactively and having the robot show us things in its own head. So how does this work? For us, a semantic scene graph takes real-world percepts, like, for example, here, this picture of a fridge, and instantiates what we call a VR belief, right? Or basically instantiates a VR scene graph. We are actually right now looking into how we can do this without prior modeling, so purely generatively. This is one of the ways in which generative AI is playing into the architecture now, that we're trying to reconstruct the scene digitally, purely without any prior modeling. But so if you have this VR belief, then you can link it to knowledge graphs. Right here, a combination of ontologies and things like the kinematic structure of the robot and other graph-shaped representations of knowledge. And suddenly you have a hybrid representation that is interpretable, right? So this entire belief state now suddenly becomes a thing that you can query. It's a knowledge base, basically. But it's not just a knowledge base, it's also a knowledge base that is sort of interactive, right? So you can change things. You can open and close the fridge door in the VR belief and see if, did the robot actually understand that this articulates this way, or that objects in the fridge are, like you can look what's in there, basically. Here's another view on this. So this is a semantic scene graph. What we are now looking into is how can we extend this to the idea of a semantic digital twin. So you take the semantic scene graph, which is our belief state, right? This is our VR belief state. The robot is kind of dreaming what it's doing in there. You have the whole environment, and you can query it like a knowledge base. But also, you have a model of robot control, which is basically a meta model of like how can we say what does it mean to, like, how does articulation work? What are the constraints on the motions? How do you compute motions? How do you motion plan? and so on. So we have actually a model of our motion planner as well that contains the kinematics, dynamics, and everything that you can then use to solve for intended consequences in the world. Right? So if you want to, for example, open the fridge and you have the robot holding the fridge, you can ask the question, how do I need to move in order to make this motion of the door happen? How can I open the door? And then we can solve for this. You can see it here, for example. But we also added to our semantic digital twin a human action model, right? That in the EASE Collaborative Research Center we are developing with our partners who are also in cognitive science, human action science, psychology. And that gives us knowledge about human actions, human preferences, human constraints, right? So how do humans actually move when they operate machinery, right? How do or where do humans intuitively put things when they set a table, right? What are the prototypes of human action, for example? And underneath, we have this idea of generalizable robot plans. This is how we translate action to robot motion. We have a structured robot programming language called PyCram that is fully compatible with all of our robots, all of our embodiments, and all of these different environments. And so now the question is like, how can we make this intelligent? Well, sure, you can like generatively generate this code, right? Like LLMs have gotten pretty good at generating code, so you can generalize a plan. But then the question is still, how do you know if that plan is actually valid in the real world? Like just because an LLM generated a plan doesn't mean that A, it satisfies your goal constraints, and B, it is safe. So for the purpose of this talk, let's focus a bit on the safety aspects, right? So how can you make sure that a generated generalized robot plan is actually safe? Well, for this, again, semantic digital twin comes in, and we can use it as an interpretability layer between our plan and the real world, right? And so when we execute the plan, what happens is we ground variables in the plan, like for example here, the object that is to be fetched, or the destination where the object is to go, or even if you have the cutting action, for example, with the PR2 and the cucumber, it's like, you know, what are the orientations in which you need to cut because you need to slice a cucumber along this dimension and not the other, and so on. So these are grounded out of our semantic digital twin. For locations and objects, we get them out of the VR scene representation. For things like the cutting direction for a cucumber, we get that out of an ontology, for instance. And this digital twin is real-time updated via perception from a real world, right? So we have the digital twin that's actually being updated constantly, so we don't make inferences about the wrong model. And then what happens if we execute this plan? Well, we first update the digital twin, see what would happen counterfactually if we were to perform this action, right? Or if we have a thing like error handling, for instance. It's like, can we predict an error occurring? And then maybe we can already do the error handling routine. And then if we notice that, okay, this is actually safe, this satisfies our safety constraints, this does not do any behavior that we don't want, then we actually parameterize our robot controller and run it on the real world. And this is basically a loop, right? So if we then update, again, with perception of digital twin, we can constantly check our constraints. We can notice, oh, is something going wrong? And then we can adapt. We can even adapt the plan. So now we're looking into using LLMs for replanning and fixing plans where we notice that, okay, they're not going to work. So how can we recover from this? Yeah, I said before that it's pretty cool to have interpretable belief states because you can put humans in VR. So now we literally start to put humans in VR. This is a very ugly first attempt. So like, excuse the ugly way that our mental robot will be moving. We haven't fully optimized the whole body control yet, so it moves strangely. But the idea here is that a human interactively teaches the robot a new skill in VR. And the human can, through speech, so the robot through speech tells the human what he thinks, and the human also sees what the robot does, and the human can take the robot and move him by his limbs and teach him how to actually do this task competently. He can take the objects and place the objects in different places. And he can talk to the robot as well. So we have this interaction with the robot belief state that we now use for, in this case, what we call interactive task learning, which is where a human and a robot together co-construct activities. And in the beginning, we assume sort of imperfect information on both sides, right? Like the robot doesn't know how to do this task safely and well, and the human doesn't know what the robot knows and wants. And so sort of the human learns how to teach the robot better, and the robot learns the thing. And here we've done this in partnership with IIT in Italy with the real AICOR as well in the real world. And so how can we take this idea of transparency and interpretability beyond the belief set of the robot and actually now go into how can we do neurosymbolic programming? And this is a bit where my dissertation comes in. So the next, 3 slides are going to be a shameless plug of my own research. But it works very well here because the idea is, okay, like if we have a robot program, like this is a robot IDE for Ultimates RPS, for instance, standard in industrial robotics, you usually have building blocks for robot behavior. But these building blocks are like, you, as a human, if you're not a total domain expert, you still have to parameterize them, right? You have to give the exact low-level parameters of, like, for example, if you do force control, what exactly the force threshold is supposed to be for this particular task, right? So let's take this program here. This is just a bigger view on this program, and it's basically building blocks that each have parameters or slots. We call this the source program because this is the program that the human actually indicated in this blocks language. And what we can then do is we can instantiate a shadow program, which we just call P bar, that's structurally and semantically equivalent, but it is neurosymbolic. What does this mean? This is a computation graph implemented in PyTorch that combines differentiable collision-free planners. So, for example, our GIS-card motion planner at University of Bremen is a differentiable collision-free planner. I used differentiable Gaussian process motion planning back then, but it's the same thing. And then deep neural networks as adaptation layers, so that you can actually, if you stick all of this together, you have a predictive model of a hybrid predictive model of what our real robot program will do if it is executed with a given set of parameters. If you run a forward pass through this, and if you've trained your neural networks correctly, you actually have a pretty good, like, even physical predictor of, like, for example, haptics and these kinds of things. We've used this for all kinds of applications, vision, force, and yeah. So that's pretty cool, right? So basically what you have down here is you have your program predicts you the expected joint trajectory, including forces and so on, for the inputs, and starts it. Right, so this is a neurosymbolic surrogate model for a robot program. Can be constructed fully automatically, so the human never sees this. That's why it's called shadow program. It just runs in the background, and it's like a digital twin of a program, so to speak. Yeah, so what's pretty cool about this is you can use this to solve a parameter optimization problem, right? So you can, you want to ideally compute the optimal program parameters that minimize some loss over your program. What does it mean to have a loss over a program? You can't compute that. If you have a program for a robot that performs something in the real world, how do you compute a loss over something that happens in the real world? You can't. The real world is not a computable thing. So what can you do instead? Well, you can instead minimize the loss over the output of your shadow program, because that's a predictive model of that program, what the robot will do in the real world if the program is executed with the given parameters and initial start state. Right, so you can do this, and you can approximate this by gradient descent because the shadow program is differentiable. So what you can do, this is called shadow programming. And so what you can do is you can do this over and over again, and you can optimize robot behavior this way, and you can execute in the real world. And if you're sort of persistent about this, you can close the loop and do this again and again and again until your robot behavior converges on something that is both like true to the real world, so your model gets better as it learns, but also the optimization forces robot behavior into like a region that you kind of want. And we use this for all kinds of use cases. What's kind of cool is it also works for, it also works with human demonstrations. So we actually used human demonstrations as a target and ended up doing this optimization to optimize robot behavior for human demonstrations. But what's cool about this from a safety perspective, and I want to go to this slide here or this slide here, it doesn't matter, is that you can, because you do this optimization and learning purely in the shadow world, right? Like you can run this, the program simulates itself. That's super cool because then if you can, again, during this optimization process, always detect, hey, does my program satisfy my constraints? And then if it doesn't, then you don't execute it, right? So you don't need to do online learning. Another cool thing is that the structure and semantic equivalence means that you always exactly know what is happening in the head of your robot, because if your robot is executing part of this optimized program, you always know, oh, this is actually now a relative contact motion, right? My parameters are this and this. I can render this. I can understand what my robot is doing because I have this symbolic representation here. That is my robot program, and I only do shadow optimization. But still, what's getting is an optimized version of this symbolic representation with optimized parameters, and you know what the parameters mean, and you know like what the constraints of these individual blocks are. A linear motion will always be linear, for example. And the last thing I want to talk about is another cool hybrid planner that we have now submitted to AICOR and are hoping that, reviews look good right now, but fingers crossed. It's a hybrid planner with this really chaotic state chart that I don't understand why the student did it this way. I gave him feedback and said this must be simpler, but anyway. Reviewers didn't care, luckily. So the idea is that we combine PDDL planning with LLM-based program generation, right? So even if you have a cool neurosymbolic program optimizer like I showed you before, the question is, where does the original program come from? The human still has to pull together all of these individual building blocks. So, and if you have an LLM purely generate that program, well, suddenly it's unsafe again, because what if the LLM generates bogus that allows the robot to run over people or runs into the wall or something? You can also, again, leverage hybrid representations to introduce safety into the mix by actually having the planner, the classical planner, a PDDL planner. That's our planner here. And you have an LLM to generate a PDDL domain and a PDDL planning problem, feed that into a PDDL planner, and then basically have another set of LLMs to check, hey, should I decompose an action? And if I decompose an action, it generates another PDDL planning problem for that sub-action. It's like hierarchical planning. And we validate that again, so we always have a plan validator in the mix. And then in the end, if we at any time come down to the lowest level of plan decomposition, we actually run it in a motion validator, which is basically a simulator in the world, and see if, okay, even if our PDDL domain and problem produces a valid plan through a PDDL planner, does that plan actually satisfy our actual task constraints? Like, does it, because it's kind of easy to trick a PDDL planner into giving a valid plan that doesn't really do anything interesting. So just because a plan is a valid plan doesn't mean that it solves your real world problem. So then we check, does it solve a real world problem? And if it failed, we, in the worst case, go back from the top and have it just generate the domain again. or we go back into other kinds of parts of our algorithm and have it critique, for example, the decomposition and say, actually, you should introduce another abstraction layer and decompose again. And yeah, so this is kind of the idea, right? PDL planner proposes a plan suggestion, the LLM, plans, we validate that plan with val, and we do it in a loop, hierarchically. And this is what it looks like in action. Again, another very chaotic state chart. But basically what happens is we do this for the furniture benchmark, for instance, right? So it says assemble the lamp. That's what the user says. We decompose this into go to the bulb, pick up the bulb, and position the bulb on the base. Screw in the bulb, go to the hood, and position the hood on the bulb. And then, for example, for the pickup action, or the composer says, oh, actually, you need to approach the bulb, you need to close the grip, you need to lift the bulb, and so on. And here it decomposes into insert and line, and so on. And one really cool thing is that if we have planning failures at any point, so we can recover intelligently because we use an LLM to reason about how did we come to this error, how can we fix it. But also, what we end up with is a plan, a guaranteed plan that is the result of a hierarchical PDL planning process, which means that given the domain, this plan is correct, right? Like this is just a property of PDL planners. Like if your domain was correct, this plan is also correct. And the domain, again, is a thing that we can even verify. Like we can, if we have a semantic digital twin and we can map from the domain to the digital twin, we can render it, we can render the start state, we can even render the individual steps that the robot does, and we can have a human look at this plan and check it. It's even possible in theory to do some model checking, but we don't do that yet. Yeah, so this is sort of a very new algorithmic advance that we're doing in that regard. I want to wrap this with a few open questions that we can maybe also discuss. First, one question is how can interpretable and sort of learned planners actually plan zero-shot, right? So right now we always have this problem that zero-shot planning tends to be a generative vibes-based activity that we do with like big neural networks. How can we actually make that interpretable? So we combine learning and zero-shot with interpretability. It's sort of not really solved yet. Other question is how can we impose hard safety constraints on such learned systems? This is maybe a bit the other direction. So what we are coming from is the direction of, okay, we take an interpretable system and we introduce learning in certain bits. There's this other direction of how can we actually have a fully end-to-end trained learned system and actually impose hard safety constraints on it. There's a big set of literature that tries to do that. Yeah, we'll see how well it goes in the real world. Another question is how can we sort of actually derive causal world models from raw data, right? So we have made a lot of advances in probabilistic learning. Actually, causal learning is still not where it could be. And how can we benchmark and evaluate embodied AI systems in human-robot interaction contexts? This is kind of, if you look into the AI safety literature, they're a lot about evals, and there's a lot of benchmarks there already. We don't really have those evals yet for embodied AI systems, for safety particularly. Yeah, and of course, autonomous long-term decision-making is still an open question that we're trying to address. With that, I thank you, and I'm open for your questions.